So, and then, we make a conjecture. Our conjecture is that the highest value possible, sorry about that, the highest value possible for J is when J is given by J1 plus J2, okay? And let's see if we can get sensible results out of that, all right? So this is our first case. J is equal to J1 plus J2. Now, since Jz is J1Z plus J2Z, this can happen if, so let's, this can happen if, hang on. Yeah. So, right. So now what we want to do is that we want to see the highest weight state, which has this, and total this J value. So the highest weight state by assumption is something which will have the M value J, and of course the J value is by assumption J, right? I'm very sorry about my kitten. He's very, very needy. So this is going to be equal to, so J1, because of this thing, of course, this is J1 by assumption. M has to be J1, and then M2 has to be J2, right? We are also assuming that J1 is greater or equal to J2, okay, without loss of generality. Okay, so is it clear why this has to be the case for the highest weight state?
I'm not quite sure, but I think I got the gist of it.
No, let's see. Yeah. So the Jz value for the highest weight state has to be equal to the total, the J value, right? So M has to be equal to J, right? This is the highest weight state.
Yeah.
But this thing is the sum of J1Z plus J2Z. So J1Z has to be J1, J2Z has to be J2. Otherwise, they will not add up to J. Because by assumption, we are assuming that J is J1 plus J2. So this has to be J1, this has to be J2. Otherwise, their addition will not give me J.
Oh, okay. Yeah.
Okay, it's as simple as that. It's not very complicated. Okay. So we are assuming that this is a state which is going to be, and we can pretty much see it's going to be the right state, but let's just do this. So there are two tests. One is we have to see what its J squared value is. So what is a J squared value of J of J? Well, J squared is going to be equal to this thing. Okay, so this complicated thing. So J squared is going to be applied to J1 cross product, or the tensor product with J2. Now, let me just copy and paste this expression. Because it'll be good to have that. Okay. So if I look at it now, see this thing, J1 squared acting on this thing will give me J1 plus 1, right? Do you agree?
Yes, sir.
And this thing acting on this guy will give me J2 J2 plus 1, right?
Hmm.
Then J1 plus acting on this, what will it give me?
J1 plus 1.
J1 plus, what is J1 plus? It's a raising operator, right?
Yeah.
So when a raising operator acts on the the highest weight state, what
Oh,
does
that's the math. Yeah. Then it's 0.
then it's 0. So we're going to get 0 from this term. Now, what about this term? We had J2 plus acting on this thing,
It's 0. Yeah.
right? And these are going to act and give me just the eigenvalue. Which eigenvalues? This eigenvalue and this eigenvalue. So it's going to give me 2 times. This guy acting on this is going to give me J1. This guy acting on this is going to give me J2. And this whole thing will be multiplying this state, J1, J1, tensor product with J2 and J2, right? You know, these operators could have changed these
Sir,
things.
I had a question.
Yeah.
Yeah, so when we apply J2 square to this state, so I was wondering how this, I mean, how does an operator act on a tensor product state? Like there is this, like
Yeah,
the
good.
J2 state.
So the J1 will act only on the first state. J2 will act only on the second one. J1 will only act on the first one. J2 will only act on the second one. Okay.
Like depending on which Hilbert spaces
Yeah,
they live
exactly.
in.
Yeah,
Acha.
yeah, exactly. Whereas this guy, it'll act on both Hilbert spaces because it's actually
It's on the tensor product
right,
Hilbert space.
exactly, because as the expression shows, it's got factors from both, right?
Yeah.
Okay. All right. So these two terms could have changed the state because they've got raising and lowering operators, but in this particular case, they kill the states. So therefore, we get an eigenvalue equation. J squared acting on this state is giving me an eigenvalue times the same state. So let me now rewrite this state. So this is J1 squared, J2 squared plus 2 J1, J2. So I can write that as J1 plus J2 whole squared, right? And then J1 plus J2. And then I can write J1 plus J2. And this whole thing will be multiplying this guy, which is just J. So we get J squared acting on J gives me, but what is this? This is J1 plus J2 plus 1 times, so I'm just, factoring this guy out, J1 plus J2. Then I get JJ. So this is J, this is J plus 1. So I can rewrite this equation as J squared JJ is equal to J plus, J times J plus 1. So we see that the conjecture passes the first test, right?
Sir, is it not also a reflection of the fact that this J follows the angular momentum algebra?
Yeah, of course. I mean, that is demonstrably true, right? It's not an assumption, right? It's just very easy to show that, right? I mentioned that earlier in the lecture today, is that, because, because here, see?
Oh, yes.
Yeah. Okay. But what we are doing here is that, of course, we know that its eigenvalue spectrum is going to be like this, but what we are doing here is that we are seeing that whether this expression acting on this ansatz, this conjecture, gives me the right result. So this tells me that the first test of this thing, of this assumption, passes the test. What is the second test? The second test obviously is the JZ. So the JZ acting on this is, it's very trivial to show. Right? It's very easy to show. So this thing will act on this thing to give me J1. This thing will act on this thing to give me J2 and then JJ. So we see that this is that J is a bona fide maximum or wait state. With J squared, eigenvalue J times J plus 1 and JZ value equals to J.